Okay, so our next talk is using hierarchical constraints to avoid conflicts in multi-agent pathfinding, and the speaker is Thayne Walker.
Thank you. I'm Thayne Walker. I'm from the University of Denver, and this is joint work with David Chan, supervised by Nathan Sturtevant. So a little context for this work. I'm a PhD student, and I'm looking at multi-agent pathfinding, and most of the algorithms to date have been tested or formulated for this four-connected grid world with weight actions. And I'm interested in extending existing algorithms to work with more complex domains. And for our research, we're looking at drones because first of all, there are a lot of different applications for fleets of drones. And secondly, it represents kind of a challenging domain that we want to tackle. With fixed-wing unmanned aerial vehicles, they're non-holonomic, which means they can't turn in place. They have to be always moving. And because they can't hover, it's more difficult for them to avoid collisions. They have to change speed, slow down, speed up. It's a little bit different problem than has been looked at before. So in general, we're interested in these challenging environments where we have high branching factors, non-holonomic movement, and non-unit time steps. And because of these factors, coupled solvers are difficult. They may have very high branching factors. They may be difficult to formulate or difficult to do collision detection with. And as I mentioned, this is earlier than other MapF experiments to date. In the multi-agent pathfinding problem, we have a graph with a set of agents where each agent has a unique start and goal location. And each agent is allowed to transition between vertices on the graph. A solution is a set of paths for each agent. And we don't want any of those agents to come into conflict. That is, they can't be at the same vertex or cross intersecting edges at the same time. And the target is to find any feasible solution. There are quite a few optimal centralized algorithms for this problem. In general, the latest research has been mainly focused on decreasing the branching factor so that we can get better run times. There are also polynomial time suboptimal algorithms, and the focus of these is just to find a solution, however suboptimal, and they also require that agents move holonomically. And there are also suboptimal variants of the optimal algorithms, and typically in these algorithms we're using inadmissible heuristics and or changing the constraints on the vehicles. So we could attempt to use some of these existing algorithms, but due to high branching factors, coupled solvers are slow. Due to non-holonomic movement, we can't use the polynomial time solvers. And due to non-unit time steps, other algorithms still need to be reformulated. However, CBS, with one caveat, is readily usable for these types of challenging domains, and I'll talk about that caveat later. But first I want to talk about the CBS algorithm. So initially we find paths for each of the agents to their goals, and then we do a conflict check. And when we're finding the paths, we disregard what all the other agents are doing. So then we do our conflict check, and if there's a conflict, then we create child nodes in a conflict tree where each of the child nodes represents a possible solution to the problem. And for each of the agents in the conflict, we place a constraint that it can't move into the same place that caused the conflict, and then we plan around that conflict. And then we do another collision check, And we continue this in a best first fashion until we find a solution with no conflicts. Now, the caveat is that there's this pathological case for CBS. And in practice, we find that there can be these large areas where two agents moving optimally will collide in every cell of a certain area in our lattice or our grid. And because CBS is optimal with an admissible heuristic, it will have to try every single combination of these optimal moves before it will try something that's suboptimal. And this can actually result in an exponential slowdown. So one of the solutions that's been proposed to avoid this pathological case is meta-agent CBS, where basically we take the two pathologically colliding agents and we put them into another algorithm to solve them jointly, and then we put that solution back into the joint solution for all agents. Unfortunately, again, because some algorithms aren't yet formulated and or high branching factors, we can't use a meta-agent to solve the pathological cases. Therefore, we come to our contribution, which is to use constraint layering to avoid conflicts so we don't have to resort to the meta-agent solver. And I'll show that this reduces the time to solution, however it yields suboptimal solutions. And it uses environment abstractions. Now, we created environment abstractions by adding additional constraints to the agents, and this is analogous to edge deletion. So basically, we're creating these edge subgraphs, and an edge subgraph is just taking away or deleting a subset of the edges from the original graph to create a new subgraph. When we create our edge subgraphs, we have to be careful to preserve the connectedness of the graph. Otherwise, we may destroy a path from start to goal for any of the agents planning on the grid. Also, there are many options with which we can create edge subgraphs. And here's an example of creating an edge subgraph. So we've taken an 8-connected grid, and we've simply deleted all of the diagonal edges to create a 4-connected grid. So we can use this process to create a set of environment abstractions. And we put an ordering over these abstractions where abstractions with denser set of edges are called finer abstractions, and the graphs with sparser edges are called coarser abstractions. So the key idea behind constraint layering to avoid conflicts is this, that when we have two agents planning on heterogeneous environments, if we formulate those environments in a good way, they can both move optimally with respect to their own environment and avoid collisions. So now we apply this constraint layering to CBS, where first we find paths for each of the agents all in the same environment. Then if there's a collision, at the same time we replan each agent, we also promote it into a finer level of abstraction. And as more collisions occur, we'll promote those agents into finer and finer levels of abstraction. Unfortunately, we cannot generally bound the suboptimality of CBS with constraint layering. And here's an example that shows why. If the red and the green agent attempt to move to their goals, on this graph they'll collide in the center. And when we go to replan these agents, the green agent will take the more expensive edge. But if we had promoted the the red agent sooner, we might have found that in a finer abstraction, there's actually an edge that goes directly to the goal very cheaply. But because that didn't happen in the right order, we returned a suboptimal solution. I'm going to show a video that shows our planning process. This is for a set of 200 agents planning between random start and goal locations. The red boxes show the bounding boxes for collision detection, and the white lines show the paths that are being planned for each of these agents. And when the planner starts, most of these edges are heading in cardinal directions, but as agents are promoted to finer level abstractions, a lot of them are changed to diagonal edges. And now I want to talk about our experimental environments. First of all, agents can turn in one of 7 different ways. They can also change altitude up or down, and they can also change between a possible 5 different speeds. Additionally, there are 20 possible heights and 8 possible headings. And looking at the branching factor, for a single agent, the branching factor is 63, and it's exponential in the number of agents. And just for reference, even with 2 agents, the branching factor is around 4,000, which makes using like A star for our meta agent solver practically infeasible. And so first, we did a benchmark on our environment abstractions. We created these 5 abstractions with various branching factors. And then we ran 100 experiments on 40 agent problems. And then we made a rule that says if we don't get an answer within 5 minutes, we mark it as a failure and throw that one away. And we found that there were 55 out of the 100 problems that we could solve in under 5 minutes for all of these abstractions. And then we tested them against our CBS with constraint layerings. And initially we found that the number of conflicts generated was significantly lower. And we base our notion of optimality against the base abstraction. And we see that the optimality is slightly better than if we just use the coarsest abstraction. And that's because some of the agents are promoted into finer levels of abstraction. And this graph shows the time to solution with varying number of agents. And in this case, we ran 100 different problem instances for each of the varying numbers of agents. And if there was any problem that took longer than 5 minutes, we just marked the solution time as 300 seconds and averaged it in. For the baseline environments, we used the same environments from the previous slide, plus the state-of-the-art unbounded suboptimal greedy CBS. And if you compare CBS with constraint layering on just the 100 agent problem, we see that on average we were able to solve for 100 agents in about 30 seconds, where the next best abstraction took 173 seconds on average. And when we looked at how many agents we could solve in about 2 minutes, we can see that we were able to solve for about 75% more agents in the same amount of running time. As ongoing work, we want to reformulate CBS-CL as an online algorithm. And we want to understand better these non-unit time and cost domains. as I mentioned before, most of the work to date has been done on these 4 connected grid worlds. We want to be able to reformulate algorithms to work with environments that represent more real-life scenarios. And in summary, CBS with constraint layering provides an alternative to meta-agent solvers for the challenging environments that we're interested in. And although it's unbounded suboptimal, it can provide high-quality solutions with a reduced running time. And that's it.
Okay, so I actually have a bunch of questions, but most of those can go offline.
Okay.
So I guess what I'll ask is the way you were trying to deal with this set of problems is by playing games. That's supposed to be a good thing. With the graphs that you're planning on, have you looked at instead mucking around with the definition of the constraints you're using? As you could, instead of defining weight constraints, you could define kind of area, or I even looked at some topological constraints. And if you play your games right to the cost, you might be able to even keep that some optimality.
Right. We have actually looked at using kind of a radius around the conflicts and changing the grids in a local fashion around the radiuses. It's not something that we were able to publish because we didn't get really good results. We found that in general, it didn't help us avoid a lot of conflicts doing it just around the conflict, because we had to actually start with a different grid in mind from the beginning of the search in most cases.
So you're taking a problem which is inherently continuous, right? And then you're discretizing it, meaning you already lose optimality, right? So I don't quite know why you're worrying about kind of being optimal in this discretization, right? I mean,
Right.
say, who cares?
What exactly is the optimality criteria? Is it the time to reach a target, or what?
The optimality we used was the sum of costs. And in this particular case with UAVs, we were using the amount of fuel to get from point A to point B. And when you have denser edges on a graph, typically you're able to proceed more directly toward the goal, which allows you to save fuel. And so that's, in that sense, we want it to be more optimal so that we can save on fuel costs or battery or whatever.
And have you tried looking at kind of a continuous formulation of this? Continuous?
Yes, a little bit, and that's part of what I plan to work on in the future. But yeah, we want to be able to use arbitrary graphs rather than just the lattices that we have, like something that you might get out of theta star or visibility graphs, things like that.
So I assume that the more you stay in the same direction and remain in the same speed, the less fuel you spend?
Yeah.
Any more questions? Okay. Thank you very much.